Okay, so this is the one that looks like, so this is rigid body kinetics. Number 14. And it looks like this. You have a wall with a hinge. And a body like this with a circle removed. And this angle here is 20 degrees. I am going to do this with a rotated coordinate system. I guess like looking ahead, since that's a fixed point at the hinge, I know that's going to be the about point of this body, so I'm going to put the coordinate system here. And I'm going to do it rotated like that just to make all the geometry easier. The one thing that then we have to think about is the angle of the weight force, you know. So if you think of so if this is the coordinate system, the weight force is this, where this angle is 20 degrees. And so the components in the coordinate system are going to be these two things. This leg is going to be, well, what's the mass of this thing? 50 kilograms. Okay, so this is going to be, the weight is going to be 490.5. And this angle is going to be sine of 20 degrees. And this is 490.5 cosine of 20 degrees. Okay. And so now you have to figure out the centroid of this thing in order to know where the weight goes. I'm going to start with a rectangle. I'll call that body 1, and then I'm going to remove the circle. That's body 2. So for the rectangle, the centroid is, you know, now finding the center of that thing is pretty easy. The was it a length of 1.4? No, 2. Okay, so we're going to go -1 in the x direction to get to the middle of the rectangle. And then we're going to go -0.35 in the y direction. And the area, excuse me, is just 2 times 0.7, so that's 1.4. And then for the circle that we're removing, the centroid is going to be, so this thing has a radius of 0.25, and it says that it comes 0.1 from each of the 3 edges. Okay, so the radius is 0.25 meters. So in the x direction, go 0.1 to get to the edge, and then go another 0.25 to get to the centroid of the circle. And so this is 0.35 negative. And then the same thing for y. You're going to go 0.1 to get to the top of the circle, and then another 0.25, so negative 0.35. And the area of the circle, you can think of that as negative, but it's going to be pi times 0.25 squared. So 0.196. And the total then is going to be 1.4 minus 0.196. So 1.204. So the total centroid is 1 over 1.204 times 1.4 times the centroid of the rectangle minus 0.196 times the centroid of the circle. So I think we get negative 1.106 and negative 0.35. Okay, so these are the coordinates of where that weight force is applied. And now let's just start going through the steps for a rigid body. So step 1, is there a fixed point? Yes. And so A is at what I chose as the origin. And now the second step is calculating that mass moment of inertia. That's a super mess again. Let's see, we have to go, so we're going to go that the mass moment of inertia about the origin is the mass moment of inertia of the rectangle about the origin minus the mass moment of inertia of the circle about the origin. So we got to figure out the ratios of these masses. Okay, so for the rectangle, we know that the ratio of the area of the rectangle to the total area is equal to the ratio of the mass of the rectangle to the total mass. And so that says 1.4 over 1.204 is equal to the mass of the rectangle divided by 50. So the mass of the rectangle is 58.14. And that means that the mass of the circle is going to be, you can think of it as negative 8.14. They have to add up to 50. Okay, so the mass moment of inertia of the rectangle about its center of mass is 1/12 times the mass times the quantity length squared plus width squared. And for that, I get 21.75. And so then we have to do the, the mass of the rectangle about that fixed point, which it happens to be at the origin where I put it, is 21.75 plus md squared, which is 21.75 plus 58.14 times, and now, okay, so here is the centroid of the, let's see. So the centroid of the rectangle, I should put another step in here. The centroid of the rectangle is located at -1, -0.35. Okay? So a vector going from the, let's say, a vector that goes from, I don't know what to call it, u, that goes from the central, oh, we're not going to need that, are we? Hold on. Yes, we are. Are we? Not really. Okay, so in order to use the parallel axis theorem, we're going to have to know the distance squared from the center of the rectangle to that origin, right? Well, since we have the coordinates of the center of the rectangle, that distance squared is just going to be, -1 squared plus -0.35 squared. Do you see that? Are you with me on that? Anybody have any questions about that? You're just always going to have to do some sort of geometrical thinking on these things. But okay, so this is going to be, I'm going to take out the negatives, but and so we have 21.75 plus 58.14 times and I get 87.01 kilogram meters squared. Okay. And then for the circle, we know that the masses have to add up to what's given in the problem, 50. So we know that the mass of the circle is 8.14. You can think of that as negative. So the moment of inertia of the circle about its own center of mass is 1, this is a circle, so 1/2 times the mass times the radius squared so this is negative 0.254. The centroid of the circle is negative 0.35, negative 0.35. So for the parallel axis theorem, that distance squared is going to be negative 0.35 squared plus negative 0.35 squared. That's the distance from the center of the circle to the pin. Okay, and then so the moment of inertia of the circle about the origin is negative 0.254 plus the mass of the circle times 0.35 squared plus 0.35 squared and for this I get negative 2.25. And so the total mass moment of inertia about the origin is 87.01 minus 2.25. And so that is 84.76. Okay. So now we can finally do a free body diagram, get on with the problem. That's just like, most of this problem is just calculating the centroid and the mass moment of inertia. So I'll just draw it like this for the free body diagram. So we have a weight force like this. And this is 490.5. And then, okay, so now we're back to sort of rigid body stuff, not just sort of geometrical stuff. There's a pin joint here. And so that's a force with an unknown magnitude, or an unknown direction and an unknown magnitude. So I'll just write that as R. And now I can write out this table. The easy one is R. Since that is at the about point, the row vector is 0. Force vector is Rx, Ry. Moment is 0. And then the weight force, that acts at the centroid that we calculated first of all. And so since our origin is our about point, the row vector, which is the vector from the about point to the object, is just the coordinates of the centroid. So that works out nice. So this is our row vector for the weight force, negative 1.1, I guess I'll round it, but negative 1.11, and then negative 0.35. Any questions about the reasoning on that? The force vector, oh, okay, well, we got to go. So this is an angle of 20 degrees. So 490.5 times for x, we have the sine of 20. For y, we have negative cosine of 20. And so this is 167.76, negative 460.92. And the cross product of those two is positive 570.34. This has a fixed point, so we're not going to use Newton's second law right now. Yeah.
The problem also has a couple.
Son of a!
How do you?
Okay. 100 Newton meters. Thank you. So we also have this couple. This stuff doesn't matter, and we just have positive 100. Okay. That's not so bad. Okay, so rotational Newton's second law says 570.34 plus 100 is equal to 84.76 alpha. And so alpha is positive 7.91 radians per second squared, which means that, we're going to need this for the next step. The angular acceleration vector is 007.91. And then it asks for the acceleration vectors at the four corners. Well, the acceleration at the fixed point is 0, so that's one taken care of. So I guess maybe I won't finish this, but the way that you would So at each of the three non-fixed corners, the acceleration is going to be equal to, this will be the watermelon equation, because each of those points is in circular motion around the fixed point. And so all you need are these values. Alpha is equal to 0.07.91. Bless you. Omega is given, has to be given. And it is -8. So 0, 0, -8. And then R is, that's depends on which corner you're looking at. But in the coordinate system I use, those are all easy, If you did all this without using a rotated coordinate system, your life was just a little more painful on every single step, and it adds up to a lot. So get in the habit of seeing problems like this and reminding yourself how happy you are you get to choose your own coordinate systems, Okay, so I think I'm going to stop there. Anybody have any other questions about that one? The reasoning on the moment of inertias or anything like that, moments of inertia? Okay.
So the centroid calculation, we only use that for the
weight.
vector of the weight.
Yeah, only for the row vector of the weight force. That's the only thing it's for, yep.
But if it didn't have a fixed point, then that would be our out point.
Yes, you should be giving this lecture. Exactly. Any other questions? All right, well, so we've been doing rolling, and so I'm going to do two examples. I'm going to do one where you see all the factors that come into, we're going to come up with an equation for like a Pinewood Derby or like a weighted cart rolling down an incline. And then we'll talk about how to use that knowledge to cheat at the Pinewood Derby, which is really why I'm doing this. Actually, my kids are both done with this now, so it's too late for me. But our last, I don't have a picture of it, but our last, my youngest son's last time with the Pinewood Derby, I 3D printed a car. It was pretty sweet. We placed pretty well, but we didn't win. But so then, I had it there's all these optimal angles for the wheels and stuff, and I just built channels to put the nails into, so everything was optimized at all the best angles that you can find online and stuff, but we still didn't win. Oh, I put a little place to put the weight, so the weight would be right at the ideal location, Because, with anyone who's used these things, it's a wood block and then you saw it. But, for this 3D printed thing, I could make it hollow, so I could put places to put the weights exactly where. How did I not win? Something was fixed.
Somebody cheated.
Yeah, exactly.
Just graphite on the angles.
Yeah, well, I put a lot of graphite on too. That is a big deal. Okay. Okay, so the way a Pinewood Derby works, let's just call this angle theta, and just weight makes this thing roll down. We'll say that the weight of the body is big M, the mass of the body is big M, and each wheel, we'll say, has a mass of little m. And first of all, to compare, if you just had a frictionless block sliding down this incline, so let's say this is mg, and then you'd have a normal force like this, and Newton's second law then says, so you'd have mg times the sine of theta, negative mg times the cosine of theta, plus 0n is equal to the mass times a0. The y equation doesn't really matter, but in the x equation you can see these m's cancel and that doesn't even end up mattering, and the acceleration is just equal to g sine theta. Okay, so we know we're going to get something smaller than that when we have it rolling on wheels. Okay, so how are we going to set this up? It turns out that you can think of this exactly the same as, think of a single wheel. There's 4 wheels, but they're all doing the same thing. So let's think of a single wheel, and the mass of 1/4 of the block on top of it, the body, is just located at the axle of the wheel. Okay, so you can think of it like that, but I thought maybe you could think of it like that, but I wanted to be sure. So I went through this whole process of, so I started out with just thinking about the body. Also, I'm going to use as I do this, I'm going to use a coordinate system like this. Okay, so this is what a free body diagram of the body looks like. Since we're looking into this, you can't see, there are 2 wheels that you can't see here, so I'm going to write this as 2 times some reaction force vector there, and 2 times some reaction force vector there. Okay. And Newton's second law says, so we have 4 times Rx, Ry, plus capital Mg sine theta, negative Mg cosine theta, is equal to the mass times A0. And again, the y equation isn't really going to matter. So this comes out to say 4Rx plus Mg sine theta is equal to Ma. Yeah.
So I fell asleep for a second.
Yeah.
Why are we saying 2R instead of just R?
Because this is a 2D drawing of a 3D thing. There's 2 wheels. You know what I mean? Yes. There's a total of 4 wheels, but I only drew 2. So I doubled them up. Yeah.
Why is the x component sign in this case?
Because of this is the weight And the components are this and this. This is mg, this is theta, and so SOHCAHTOA. So this is mg sine theta. This is, the component is negative, but this is mg cosine theta. And you'd also get that from the rotation matrix if you did it that way. Okay, so we got this equation. And now we'll go to one of the wheels. And this is where we're going to use rigid bodies. Okay, so what's happening at the wheel? Is there a fixed point on the wheel as it rolls down? There's a point fixed to the body, but not fixed in the coordinate system. And there's the point in contact with the ground that has zero velocity, but it doesn't have zero acceleration. So no, there's no fixed point. And so the about point is the center of mass of the wheel. Okay. And what are we going to call the moment of inertia? I didn't say anything about it being necessarily a disk. Let's just say that, let's keep it pretty general, and then we can think about different shapes later. So this is going to be 1/2, no, that would be if it was a disk. Let's just call it some constant c times the mass times r squared. That's a pretty general description of a rolling thing. You know, that works for a sphere, it works for a ring, it works for a lot of stuff. And so then it works for any sum of all those things too. And now let's do the free body diagram. There's a weight force down of little mg. There is negative r, okay, because of Newton's third law. This r, this reaction, where did I draw that? For each one of these wheels, that r is the force that's applied to the body by the wheel. Okay, and so the force that's applied to the wheel by the body is negative r. Then there's a normal force. And a friction force. And that friction force is what makes it roll instead of slide. And then we can do a table. Well, negative r our about point is the center, so rho vector is 0. The force is negative rx, negative ry. Cross product is 0. Next is, let's do the normal force. The vector from the about point to where that force is applied is, oh man, I have this r here. Well, I'll just call the radius little r. So it's that in the coordinate system. the force is 0n, and so the cross product is 0. I better make this little r also. Then the force of friction, the row vector is 0, negative r. The force vector is negative ff0. And so the cross product is negative rff. And then the last one is the weight. Row vector is 0. The force vector is mg sine theta, negative mg cosine theta. And the cross product is 0. This doesn't have a fixed point, so we have to use Newton's second law. So Newton's second law says negative rx, negative ry. I'm just going down the column of all the forces. Plus 0n plus negative ff0 plus mg sine theta, negative mg cosine theta is equal to the mass of the wheel times the acceleration. And the one we're going to use is the x component of this equation. So, okay, we have this so far from the body. And now I'll call that equation 1. And now from this, we have equation 2. How would you know, by the way, like, I kind of glossed over this because I've already done this problem, but how would you know that you're not going to use the y equation? There's not really any way to know. What you would do is you would get your whole system of equations, and then you'd see, like, I don't even care about the stuff that's in equation 2 and equation 4. So then you just forget that, cut down the number of variables, and cut down the number of equations. Okay. Okay, so the second equation says negative rx minus ff plus mg sine theta is equal to ma. Okay. And then we have the moment equation. So add up all the moments in the moment column of the table. It says all we have is negative rff is equal to the mass moment of inertia, which is so c m r squared times alpha. And so this is our third equation. Okay, can we solve it yet? Well, you can figure that out by just counting variables and counting equations. We have 3 equations, and for variables, we have Rx. Now, the M's and the G and the theta, those are all constants that would be given. Okay, so those aren't variables. So Rx and A, so that's two variables, and FF, so that's three variables, and alpha, so we have four variables. So we need one more equation. What would you guess we're going to use for another equation for this problem in a section called rolling without slipping? So we're going to use the rolling without slipping relationships between acceleration of the center and the angular acceleration, okay? So from rolling, we know that the acceleration A0 is equal to negative alpha r 0. That I'll give you that equation on tests and stuff, but we're using that all the time. And so our fourth equation says A is equal to negative alpha r. And so now we have four equations for four variables. We didn't come up with any new variables in that equation. Yep.
Can you remind me what C is in our?
Oh, yeah. Well, so remember that for a disk, we have 1/2 mr squared. For a sphere, we have 2/5 mr squared. For a ring, we have, oh, come on, mr squared. And so that's just saying these all look the same. All that changes is some constant, so that's just that constant. So we can plug in a 1/2 to represent a disk, 2/5 to represent a sphere, other things to represent other combinations of these. Any other questions right now?
I don't know,
Yeah.
or if you go to the equation for the wheels, down to equation 2, because that's equation 2, that's the wheels, right?
Yeah.
Would mg, is it 4 wheels, would that be divided by 4?
Oh, I got you. We divided each wheel as a mass of m.
Okay,
So
the mass of the wheel.
that's the mass of a single wheel, yeah.
Got it.
But the big M is the mass of the whole thing. So we're going to see this big M over 4 floating around as we start solving this, because that wheel's only taking 1/4 of the mass of the whole thing. But we're going to see the full little m. So that all just comes from how we're setting it up. Okay, so now, I mean, really all we're doing now is solving that system of equations, but I'll do that next time. But, you know, hopefully you can see just, I mean, really the part that's useful for getting used to doing rolling problems, rigid body problems, we've already seen. Now it's just sort of some math and rearranging stuff. But we'll come up with an equation that says, okay, this is how the mass of the thing matters for the acceleration. This is how the mass of the wheels matters. This is how that C value of the shape of the wheels matters. Any other questions? Okay, so continued next time.